So exceptions to electron configurations. Where do they occur? What are the exceptions that you have to be aware of in this course? Where the exceptions occur are here, so chromium, molybdenum, tungsten, and here, copper, silver, and gold. That is where the exceptions occur. So before we talk about those exceptions and the rule that governs them, let's look at an example. Let's look at chromium, one of the exceptions. So chromium, and we'll use the shortcut or the shorthand for writing its electron configuration. So if chromium is here, what you can use is the preceding noble gas as the noble gas core. So chromium is 24, argon is atomic number 18, it precedes it. We can use that to abbreviate all the electrons up into this point. And we put it in brackets like so. And then argon, 4s1, 4s2, 3d1, 3d2, 3d3, 3d4 is what you would predict. Excuse me, I should write 4, 4s2, 3d4. That is what you would predict. Okay? But it turns out through experimental measures, that a full d or a half-filled d orbital is lower in energy than a completely full s orbital. So for the exceptions, a half-filled d orbital is favored over a full s orbital. So the actual configuration for chromium is 4s1, 3d5. So those columns have exceptions. Again, why? The rationale that this half-filled d orbital gives a chromium atom a lower energy, and therefore more stability, than a full s orbital. Okay, so half-filled d orbitals. Another exception, another example is copper. So can we use argon as a noble gas core, which you would predict? Four s1, 4s2, 3d1, 2, 3, 4, 5, 6, 7, 8, 9. That's what you would predict. But the actual configuration for copper is 4s1, 3d10. So a full d orbital is lower in energy than a full s orbital. So when you see these areas where you have a half-filled d orbital or a full d orbital, that's where you have to take an electron from the s orbital, as you would predict, and it will go to fill the d orbital, or half fill the d orbital. Electron configurations for ions. So what do you do for ions? Well, first, you have to determine what the electron configuration is for the ground state, that is for the normal electron configuration, the ground state electron configuration. So if we look at potassium, and we use its noble gas core abbreviation. So potassium is here. Argon is its noble gas core. Immediately precedes it. And then 4s1. So the valence electrons, that is the outermost electrons, the one that has the highest principal quantum number, those are the electrons that are going to be removed first. So remember from earlier in your chemistry courses that potassium forms a cation. So potassium cation will adopt a noble gas configuration of argon. And the 4s electron would be removed, would be the one that would ionize when potassium becomes a cation. Okay? So what do you do when you have something a little bit more complicated? So a metal such as chromium. From our last segment, it's one of the exceptions. Its noble gas core is argon as well. It's 4s1, 3d5. That's its normal ground state electron configuration. So if you have something, if you had chromium plus which electron is removed or ionized first? The rule is such that the 4 is the higher principal quantum number. That's the higher energy electron. That is the electron that goes first. So 3d5 describes a chromium cation. What about chromium 2 plus? (3d4). So it's again one electron at a time. Chromium is multivalent or polyvalent, meaning it can form multiple oxidation states. If you had chromium 6 plus, it would adopt its noble gas core of argon. Okay. Chromium has 6 valence electrons, so we're called transition metals. Depending on the rules that you observe, the valence electrons are the S and then the N-1d electrons. So 6 valence electrons, 6 plus charge, adopts the noble gas configuration. So the principle is, for cations, the highest quantum number electrons are the ones that are ionized first.